We talked about acids, and now we're going to talk about bases. So a strong base is one that dissociates completely. Remember, bases produce hydroxide ions or accept protons. So the hydroxide concentration of a strong base is equal to the concentration of the base. Most strong bases are going to be group 1A or 2A metal hydroxide. Hydroxides, things like lithium hydroxide, sodium hydroxide, potassium hydroxide. The ones you have to watch out for in terms of the hydroxide ion concentration is things like strontium, calcium, or barium, where you have 2 hydroxides per unit of barium hydroxide. And so there probably is a question on the exam that's going to try to trick you with that. Okay, so I've just warned you, then it's not a trick, right? Yeah, you got to watch out for those. Because if you had 1 molar barium hydroxide, it would have 2 molar hydroxides, right? Well, yeah, I get ahead of myself. The group 1A metal hydroxides are highly soluble, so you can form concentrated bases. The group 2 metal hydroxides are only slightly soluble, and as I just talked about, they produce 2 moles of hydroxide. These metal hydroxides dissociate in 1 step. So it's an ionic compound, it just dissociates. So it produces all of its hydroxides at once. This is different than like a diprotic acid where it loses 1 hydrogen and then it loses another one and you have 2 equilibrium constants. So a weak base is like a weak acid. Most of the common weak bases produce hydroxide by accepting a proton from water. So here we have our base, B, not boron. Base plus water, the base will accept a hydrogen ion, and that produces the hydroxide. So ammonia is a weak base that you should recognize. Ammonia is NH3, and in water, it's going to accept a hydrogen ion from the water molecule to form ammonium ion and hydroxide. Okay, ammonium ion and ammonia are substances that you learned the names and formulas of in Chem 1A, and so I expect that you still remember that. Any questions yet? So weak bases only dissociate partially, like the weak acids, and so there's an equilibrium constant. So Kb is called the base ionization constant, and it quantifies the strength of a weak base. So here's our base reacting with water. Then Kb is going to be the products divided by the reactants. When we do this with a base, we have to include the H2O here because that's where the hydrogen's coming from. When we do it with an acid, we often just, to make it faster, we'll just say HA, and we've got H plus and A minus. Just understanding that this is not actually H plus, it's H3O plus, instead of writing the whole thing out. So that's what we mean. We often leave the water out in a weak acid equilibrium. We can't do that in a base because we need the hydrogen from that water molecule. So if Kb is small, that means it does not go very far to the products, which means it's mostly just the base waiting to act as a base, and so it's going to be very weak. If Kb is large, it goes more towards the products and it's stronger. So large Ka, stronger acid, large Kb, stronger base. And then we can also talk about pKb, which is just the negative log of Kb. Any questions? Here's some weak bases, their ionization reactions and their Kbs. Carbonate ion is a weak base. It can react with water It'll accept a hydrogen ion and form hydrogen carbonate ion and hydroxide. So that's a weak base. And that's something that you might not recognize as a weak base. The hydrogen carbonate ion that it forms, HCO3, is also a weak base. It can accept another hydrogen from water and form carbonic acid and hydroxide. So that's one that you should be aware of and be able to recognize. The other ones that you need to be able to recognize are amines. And so these are organic compounds that have ammonia in them. So ammonia is NH3. These are all relatives of ammonia. So here's ammonia, NH3. Methylamine, what has happened is we've removed one of these hydrogens and replaced it with a methyl group. The nitrogen has a lone pair. That lone pair is what accepts the hydrogen ion from water, producing the hydroxide. So this is a weak base. Ethylamine, we've replaced one hydrogen with an ethyl group. Pyridine and aniline are cyclical structures. I would not expect you to recognize them as bases from their names, but I would from their formulas. So if you see a formula that has C's and H's and an N, that's a weak base in this class. Okay? Everybody okay with that? I got ahead of myself again. Yeah, I drew this for you, and here it is again. Okay, so here's ammonia. That lone pair is what acts as the proton acceptor. So it can accept a hydrogen from the water to form ammonium ion and hydroxide ion. This is methylamine. It's got a methyl group, CH3 here. And the nitrogen, again, is acting as a weak base because it can accept a hydrogen ion. So the hydrogen ion from water comes over here to the nitrogen, and we've got this guy. So it gains a hydrogen and has then a +1 charge. And so that's what all of them do. They'll gain a hydrogen and have a +1 charge. Any questions? So finding hydroxide ion concentrations and pHs. If you've got a strong base, the contribution of the autoionization of water is negligible. We just ignore it. So then that's not a problem. If we're looking at a weak base, we can find the hydroxide ion concentration and eventually the pH in a very similar way to what we did for weak acids. I learned about this last week. We're going to neglect the contribution of the autoionization of water, almost always too small. I'm slow today. Make a nice table, use the Kb expression to find the hydroxide ion concentration. If you need the pH, then you just go around the circle of pH until you get there. Let's do an example. This is a strong base. So do we need a nice table for a strong base? No, we don't. You don't necessarily have to write this out, but I think it's a good idea. So this is going to dissociate in water and form hydroxide ions directly. That's what strong bases do. This is not an equilibrium arrow, it's a single arrow. This goes to completion. So if we want the hydroxide ion concentration, we can just take the barium hydroxide ion concentration. Now let's do it this way so nobody gets confused. and do stoichiometry. So we can write the equation for the dissociation of the strong base, and we can calculate it like this using stoichiometry. We know the concentration of the base, and we know there's 2 moles of hydroxide for every 1 mole of the base. Do you have to write all that out? No, you don't. But that's kind of the thought process behind it. In this problem, you'd need to notice that there's a 2 here, and so you're going to multiply this concentration by 2. So that's the hydroxide ion concentration. Then we need to find the pH. I didn't give you an equation relating hydroxide ion concentration and pH. I showed you this circle of pH, right? So what I prefer to do is first find the pOH. So the pOH is the negative log of the hydroxide ion concentration. And that equals 1.69. Our molarity here has 2 sig figs because the starting molarity had 2. And so this pOH is going to have 2 significant figures. Remember, in a pH or pOH, it's the decimal places. Yeah, question?
So for strong bases, is the pOH plus the pH always 14, because that's kind of what it is.
Yeah, pH plus pOH always adds up to 14. Doesn't matter if it's a strong acid or base, weak acid or base, it's just always true. It's really a property of the water itself. So 14 minus that. $12.30103, 12.30. Any questions? Okay, here is a similar question but with a weak base. So find the hydroxide ion concentration and pH of 0.33 molar methylamine solution. They give us the Kb. They don't give us the formula for methylamine because we don't need it. We can just call it B. B for base. So the base is going to react with water, and it's going to form the conjugate acid plus hydroxide ion. Okay? So what's really going on here, this methylamine has a nitrogen with a lone pair. That lone pair is what is going to hold on to this hydrogen ion. Remember, the base is like the babysitter. It accepts the baby from the adult, the acid, right? So it takes the baby and holds on to it. It's that lone pair that allows it to do that. So that's our chemical equation, and then we need an ice table. ICE. And then we're going to go with initial concentrations first, right? They tell us the concentration of the methylamine. Well, that's the B. So 0.33 molar. What about the H2O? We don't care. That's a pure liquid. I didn't write the state symbols here. That's what they would be. Right. So we're not gonna do anything with the H2O. What's the initial concentration of BH plus? 0. And the hydroxide? Also 0. Technically, approximately 0. And then how's this gonna change? It's gonna have to be minus X over here and plus X over here. These are at 0, you can only go up. Then you add your I and your C rows. And I don't have enough room here, and I've got too much room on the other side. 0.33 minus X, X, and X. We've been doing a lot of ice tables. This is the second chapter with ice tables, and there's one more coming. So if you have any struggles with ice tables, please come and ask me about it. Once you see how they work, it's pretty simple, but it can be a bit of a journey to finding out, being able to see it. So I'm going to write my KB expression. And then I know what KB is because they gave it to me. I'm going to start writing up over here because I'm running out of room. So 4.4 times 10 to the minus 4. And that's going to equal BH plus times OH minus. So X times X. X squared. Divided by B plus 0.33 minus X. Bless you. We need to solve for X. Does this look like a reasonable candidate for X is small? Yeah, probably. 0.33 is relatively large and 0.44 is relatively small. So you could do that. Then you have to check it. I'd rather just do the number solver myself, because then you don't have to check it. You just know that's the right answer. So 4.4 times 10 to the minus 4. It's kind of a cool one. And then up top I have X squared, and in the bottom 0.33 minus X. X equals 0.01183. Any questions yet? What does X represent? The change, and also the equilibrium concentration of hydroxide ion. So this is the hydroxide ion concentration that we're looking for. Then we need the pH. You can convert this to hydronium ion concentration using Kw, or you can just do the pH plus POH equals 14. Yeah, question? Your calculator's not giving you that answer? Bless you. Okay, so what I'm going to do is I'm going to find the POH of this. So that's the negative log of what I just calculated here. Oops, that's not what I wanted. So 1.9269, because that should probably have two sig figs. And then the pH will be 14 minus that. .0731, 12.07. And peeking ahead, the book gives us slightly different answers. And why is that?
They use the
They used
excess.
X is small. Does that mean we did it wrong? Nope, it's fine. There's just a small difference in the uncertain digit, not a problem. Any questions?